Okay, so this here, f prime at a, we call that what? Derivative. Okay, we call that the derivative.
Can you make it bigger?
Now these two are exactly the same in different form. They're both derivative. Two popular forms of derivative. So what's the difference between these two expressions and this one? They look very identical, but there's one big important difference. What is that difference? Yes, this is x. This is a constant. This is a variable. Meaning, we interpret this as a function or a particular rule which will pump out answers for us. This is a particular instance of an answer. Okay, so the main topic of 2.1.2 is, well, when does derivative exist? Okay. The derivative is an extension of limit. So, you guys recall, when does limit exist? The left-hand limit and the right-hand limit must equal to each other, right? So in this case, it's left-hand derivative must equal to the right-hand derivative. And what does that mean, though? Okay, so let's switch the word derivative with slope. Left-hand slope and right-hand slope must be the same. So what does that result for the graph? Yes, they have to be nice and smooth. Right? The slope is, the tilt is approaching the same value. So do all graphs have to have the same tilt as it approaches a particular number? So an example of non-smooth graph will be cubic function? No, it's all smooth. When I say smooth, I mean like even if you zoom in, when you zoom in, it's smooth. Right? So like here, whether you approach from the left or right, do you see that the slope is approaching the same value? So when does it not approach the same value? No matter how much you zoom in. What about there? The slope left side is consistently positive 1, right? What from the left side? Consistently, it's negative 1. Suddenly, right here, it switches to positive 1. This is a case scenario where the derivative does not exist. Of course, it doesn't have to be a nice line like this. It could be like this. Alright, these have a special name. Graphical name for these characteristics is called a cusp. So where is a function differentiable? Where does it have slope? Right? An instantaneous slope. It's everywhere except for x equals 0 because of that function looks like this. If you were to show it numerically, this is how you have to do it. The left-hand derivative will be the following. So here you have to be picky with the h. It's f f at 0 minus f at 0 minus h over h. So we're taking this y value minus a number to the left, which is minus h here. Okay, so what is that going to approach? Let's plug it in. You get this. And we get minus of h over h, so it's equal to negative 1. The right-hand derivative will look like what?
Don't you have to put plus and negative sign?
So the right-hand limit will be this, f at 0 plus h. So we want to vary to the right, right? And then squeeze that into the origin. And this is going to give you 0 plus h absolute value minus absolute value of 0. So you can see it's going to be h over h, so it's equal to 1. Okay. So look, it's different. So let me generalize that a bit. Okay, so we have a, and let's consider, we want to talk about the right-hand limit. So right-hand derivative. So the slope that's approaching from this side. So it's, look, it's becoming more like negative, right? More sort of positive from the right side. And from the left side, it's positive, but it's becoming smaller. Do you know what I mean by that? The slope here, like the value is like 2, and then it's like 1, it's like 0.5, and shrinking. Here it's like 0.2, but it's increasing. But they're both increasing to a particular same slope value right there. Okay. So the left-hand derivative, more generally, is written this way. H is approaching 0, f at a minus f at a minus h all over h. The right-hand derivative will be f at a plus h minus f at a all over h. Okay, so take a look here. The left-hand limit, this is fixed. I move this, right? So that's f at a. That's f at a, right? Let's assume h is positive number. So we got to subtract h. Right? So this is a minus h, right? If that magnitude of that distance is h. Right? That's why we do f at a minus f at a minus h. In the other way, that's h again. This is a plus h, right? So the definition of derivative that we've been using is sort of equivalent to the right-hand derivative, but that one, when we're doing that one, we actually interpret h as not strictly positive. We think of it as positive and negative. It can be either. Then it becomes squeezing from both sides. Here we set h to be positive. Then this becomes the left-hand derivative. This is the right-hand derivative.